Good afternoon, everyone. I'd like to welcome you all to Breaking Hardware Enforced Security with Hypervisors here in Lagoon Cay. Speaking with us today is Joe Sharkey. He's the Chief Technology Officer at Siege Technologies. We have a couple of housekeeping items to go over. Don't forget to stop by the business hall located in Bayside A and B. Black Hat Arsenal is on in the Palm Foyer, level 3, and the Arsenal reception will be at 5 p.m. If you haven't picked up any merchandise, the Schwag and Bookstore will be closing today at 5, so swing by. You can still visit Kali Linux Labs in Mandalay A, and if you would, please put your phones on vibrate or silent, and welcome Joe.
Thank you. All right, so I'm excited to be here today talking about breaking hardware enforced security with hypervisors. We're going to talk about a couple of different technologies, and we're going to break both of them with hypervisor rootkits. So specifically, we're going to be talking about Intel TXT and AES-NI, which are both hardware primitives that were added in the hardware to help enhance security. We're going to show how they can be compromised and undermined. So I'm going to start with a little bit of background on the technologies that we'll be covering today. Then I'll talk about how we can use the hypervisor rootkit to undermine TXT, talk about undermining AES-NI, and we'll wrap up talking about implications and some kind of takeaways, near-term solutions. What are things that we can do walking out of this session today to kind of make our systems more secure? All right, so I'm going to start by talking about dynamic root of trust measurement, or DRTM. So DRTM has become the trusted computing paradigm for servers, laptops, PCs. So this is called dynamic root of trust. The alternative is static root of trust. That's what we see on like iPhone, gaming consoles, things like that, where it's like one vendor that controls all of the code, controls the hardware, and they can check digital signatures of every piece of code that executes on that platform from like the very first instruction all the way up and through. The problem is that paradigm doesn't work very well for a PC style platform because it's not all controlled by one vendor, right? There's a lot of different components in there. You've got the motherboard with BIOS. Maybe it's an Intel motherboard. BIOS was written by Intel, but it was modified by your OEM, right? Adapted by like Dell, HP, Lenovo, whoever. And then you got video cards, network cards. They all run firmware too. So collecting the signatures of the right code for all of that just becomes an insurmountable problem. So Intel came out with this alternative of dynamic root of trust. Allows you to establish this root of trust some point later in the boot process. So it doesn't have to be from the first instruction. And the assumption is that at the time you're starting or launching this process, the system could be in completely untrusted state. There can be malware running, right? You have to assume you're not in a good state. And what we want to do is be able to put the system back into a trusted state, and from that point be able to load our trusted operating system or trusted hypervisor and know that the system's in a good state. So part of what that includes is an atomic instruction to do this, quote, measure and launch to kick off the process. Literally one assembly instruction starts the ball rolling for establishing the root of trust. And Intel has released some open source tools to help work with TXT. And so they have some tools like inside of Linux, some operating system, like kernel modules to interact with the hardware, and then some user space tools to check the state, to say, did I reach a trusted state, did I not, and check the status of what's going on. And so the large code base that is open source and implements TXT is called tboot, and it's largely written and maintained by engineers and developers at Intel. And it's kind of the de facto standard. If you want to use TXT, tboot is probably what you're going to do. And so tboot can load straight out of Grub, and you launch tboot, and then from that it can chain load your operating system or trusted hypervisor. So it like works with Zen or VMware ESXi, that sort of thing. And so the idea is it's taking measurements during this DRTM process and then kind of checks that against a known state, right? And says, all right, so I tried to enter this trusted state. Did everything work out? If so, cool, let the system boot, indicate that we're in a trusted state. If it doesn't work out, if for some reason we can't enter that trusted environment, we can't launch successfully, then it falls back to a policy that's configured when you set it up and install it. And there's a set of policies you can do, launch control policies, and they can be really strict, and they say like halt the system, don't let it boot if anything goes wrong. Or they can be a lot more relaxed and allow the system to continue to boot all the way up into your operating system, and just make note that you're not in a trusted state. So like those utilities inside of Linux will let you know the system's not in a secure state. So in order to do this, there's a set of hardware extensions they added to the system. It starts with instructions in the CPU, the SMX instructions, specifically getsec and getsec senter, which is like a leaf function or sub-function within there, is what we're going to talk about a lot today. So getsec senter is the instruction, the single assembly code opcode that kicks off the root of trust process. In addition to those CPU extensions, there's a bunch of other additions that go into making this happen within the chipset. So there's VTD protections. Oops. Back one slide here. VTD protections that guard against DMA attacks during the establishment of a root of trust. There were specific bus protocols, a new version of the LPC bus that has special bus cycles that indicate the trusted state from within hardware, signaling across to the TPM. And TPM is a critical part that's going to store these hashes, store the measurements, and help provide some attestation. So there's a whole set of changes to the system that had to be made to implement this. I do want to note, although I'll be talking about Intel specifically today, AMD does have a similar implementation. They have their secure virtual machine. Their instruction is called SK init, secure kernel init. And it works very much the same way. All right, so the last background I want to cover is about the TPM and how it's used as part of this process. So TPM is a really cool piece of hardware, secure coprocessor, and it provides like a whole set of features. I'm going to cover the ones that are specifically relevant to dynamic root of trust today. So the first thing is PCRs, platform configuration registers. So these are the registers that store the hashes of the code and system state that make up your trusted computing base. Something important about PCRs is software can't just set them to a value, right? So there's a set of them. You can't just say set PCR 17 to a value of 1, 2, 3, 4, 5. That's not how it works. The only way you can change the value is through what's called an extend operation. So the extend operation takes the current value in that PCR, concatenates the new data you want to add, and then takes like a hash of that whole thing. The result of the hash becomes the new value of the PCR. Right? So you can keep extending them over and over and over, and it's going to change that value. But it's computationally infeasible to set the PCR to a specific value. Right? I don't know what I need to extend it with if I want the result to be 1, 2, 3, 4. And that's really important. It's an important feature of the whole technology. And then order of operations is important, right? It's, extending with A followed by an extend with B is not the same as extending with B and then extending with A, because of this, the way the concatenation and hashing works. And so there's a set of these PCRs. Some of them are used for static root of trust. The ones relevant today are number 17 to 23, which are specifically used for the dynamic root of trust. All right, so now the PCRs store those measurements. There's another set of important features the TPM provides called sealed storage and remote attestation. So what sealed storage does is it allows you to bind data or seal data in the TPM and seal it against specific values in the PCRs. So let's say we're going to seal data against PCR 17, 18, and 19. When we seal it, it looks at the values of those registers, and it will only allow us to unseal that data when those PCRs are in the same state they were in when we sealed it. So you kind of think of those PCRs as like the combinations to your combination lock, right? And when they're in the right state, you can open that safe and go in and take out your secrets, right? But if you put them in there and you spin the dial and the TPM's not in the right state, it's not going to provide you access to those sealed secrets. Remote attestation works conceptually the same way, but allows you to attest to a remote entity. So basically a different system. It allows the TPM to provide a quote with its own private key that's locked in storage and can only provide the right response when the PCRs are in the right state. All right, so we'll come back and talk about these a little bit later. So this is not the first talk that looks at undermining TXT. There's been a bunch of work here. So just want to point out some of those. If you're not familiar with these particular things and you're interested in this stuff, I encourage you to go look up this work. Some really, really great stuff. Invisible Things Labs looked quite a bit at TXT a few years ago. And they showed that you can use system management mode to bypass the root of trust measurement because it's not included in the measurement. Intel talked about this STM, secure transfer monitor, that can actually measure what's in system management mode, but we're still yet to see a real implementation of that in practice. Then there's a couple of other misconfigurations in chipset registers and some bugs in this authenticated code module, which is code that's signed by Intel, that's part of the launch process. So a couple of different bugs like that allowed the TXT to be subverted. And those have been patched. There's new signed modules released and some microcode updates that as long as you're running the newest microcode, it won't let you, load the vulnerable versions of those AC modules. And there's some other work looking at hardware attacks against TXT. Jonas Winner showed that you can open up the case, connect onto the LPC bus, and actually inject some signals on the bus that gets the TPM to reset state, gets those PCRs back to a value of 0, that then allows you to do the extends you want to reach the value you want. Again, very interesting, requires physical access, requires opening the case, connecting in. And so what we want to talk about today is how can we circumvent TXT completely from software standpoint, and in a way that it could be done, remotely. All right, so what we do is I call it the SNer emulation attack. So we talked about that getsec SNer instruction as being critical for establishing this root of trust. And so what we do is, coming out of Grub, instead of loading tboot, we're going to load our own custom hypervisor, so like a thin hypervisor rootkit. And our hypervisor is going to virtualize all of the SMX instructions. It's going to provide a virtual TPM so that the rest of the software on the system can actually talk to the physical TPM. And it's also going to virtualize the whole TXT memory mapped I/O space. So all of the chipset features that are queried to check the status, we're going to virtualize all of that. And pretty much then we're going to lie through our teeth, right? So we're going to intercept what tboot is trying to do, lie to them about the state, tell them, yep, everything is cool, go ahead and boot. And during this whole thing, they've never actually run getsec SNer on the hardware. They've never put the hardware into a trusted state. And they've never really unlocked any of those secrets out of the TPM. So, all right, how do we do this? How do we know how to emulate all that stuff the right way? So start by looking at the SMX instructions, and conveniently, when you look at the Intel Developer's Manual, they give you pseudocode for this instruction on what it's supposed to do, right? And it's a complex instruction. The pseudocode is several pages long, but we just take that pseudocode, right, convert it to C, and then obviously, ignore some of the security checks we don't want to do. But that allows us to emulate the instruction in a way that's close enough to what the real hardware does that tboot is fooled, but skipping all of the important security stuff it's doing. So then there's this authenticated code module that's supposed to be the first piece of software run. And so we have a couple of options with the hypervisor rootkit. And I actually was able to implement it both ways. We can run that AC module inside of a virtual machine we control and kind of let it execute and filter out some of the operations it's doing. But we also found we can just skip it altogether. There are some side effects of doing that. The AC module is supposed to put the chipset back into a trusted state. It's supposed to go through all of the important hardware and initialize it properly. But we're actually able to skip that, and T-boot doesn't know the difference, and Linux doesn't know the difference. And we emulate all interaction with the TPM. So before we had, like the real TPM has these extend operations for the PCRs, and so we can emulate all that. But for ourselves within the rootkit, we can just set those PCRs to the value we want. And then when someone reads the values, we can return what they expect it to be, and never let them talk to the real TPM. So the bottom line is, the software on the system really believes it's in a trusted state. It believes that the DRTM measured launch succeeded. So it doesn't matter what launch control policy you set at that point. Right? You can have the most restrictive policy telling the system to halt, not continue booting if something goes wrong. It doesn't reach that policy, it doesn't invoke that policy because it doesn't believe anything has gone wrong. It truly believes the system is in a good state. All right, so I'm going to hop over to a video I have for a demonstration. First going to explain what you're going to see. We're going to see a system boot without using T-boot, just a normal system boot. And we'll just kind of see how these utilities in Linux, txtstat, and looking at the PCRs show the system's not in a trusted state. Then we'll see a system with normal T-boot, current version, booting up, and we'll see what it looks like when it is in a trusted state. We'll see that the PCRs have some values that are specific to my system here. And then we'll see it booting with the hypervisor rootkit. Come up and we'll see you get the same output from the command line utilities. Right, so how we're going to know the rootkit is running, what I did is implemented some serial port output. So the hypervisor rootkit's going to like print some things over the serial port to show that it's running, explain what it's doing. T-boot also prints out on the serial port, so that's kind of cool. When it's running, we'll be able to see the T-boot messages coming along with some messages from the hypervisor rootkit. See. Where did my mouse go? All right, there we go. All right, so measured launch is false for normal system. We can see PCRs 17 through 23 are initialized to -1. Now let's see what it looks like launching T-boot. And we can see T-boot prints a bunch of messages across the serial port as it boots, explains what it's doing, shows some measurements. Now when we run txtstat, we see measured launch is true. And if we look at the values of the PCRs in the TPM, we'll see that PCRs 17 through 19 have values that were initialized by T-boot. So now let's run the rooted T-boot. This is going to launch the hypervisor rootkit first. And we can see some output from the hypervisor rootkit. Then it's going to launch T-boot, and we'll see messages interspersed there between T-boot and my hypervisor rootkit as it's emulating those operations. We see all the TPM access is being completely emulated. Linux finishes booting, and now we can come in and run txtstat, and we can see it says measured launch is true. And if we look at the PCR values, they have the same values as before. So to show that, ran diffuse, and kind of hard to see all the numbers there, but you can pull up the slides afterwards and take a look at it. And it, oops, a little bit too far. There we go. But what we have is the same exact value. So as far as the software on the system is concerned, we're in the same state that we were with regular tboot, right? So completely undermined the root of trust here. So then the question is, should this kind of attack succeed? It's like, well, hold on, Joe. Like, you didn't actually run the instruction, right? So, is this really in scope for the kind of protections it's supposed to do, right? Like, as long as it runs the instruction, everything's cool. I made sure it never really started that process at all. So interesting thing, this graphic on the right comes out of Intel's white paper talking about TXT, and circled in red, they specifically talk about the case of a rootkit hypervisor as the example quintessential test case threat model that they're defending against, and specifically say that hypervisor rootkit or rootkit hypervisor will be detected and the measured launch will fail. And I say that's true if you ever actually start this process in the hardware. Unfortunately, with the hypervisor rootkit, it's able to virtualize all of this, so there's no guarantee that that ever actually happened. And there's one caveat to that. We talked about sealed storage in the beginning as a feature of the TPM. When sealed storage is used properly, it can actually detect and prevent this kind of attack. We'll come back to that towards the end. We'll talk about what's the right way to do this. But unfortunately, sealed storage isn't used by tboot. It's not used by default, and it's not really even an option. There are some command line utilities in Linux that allow you to seal and unseal data against the TPM, but it's kind of left up to like the sysadmin that's configuring and installing this stuff to like figure out what secrets they want to seal. And all of the instances I've seen with this hasn't been done right the first time because the sysadmins don't really understand what they should or shouldn't be doing with it. So again, we'll come back to the recommendations at the end. But the fundamental problem here is that these instructions are virtualizable. So the SMX instructions, by default, cause a trap, a VM exit to the hypervisor, right? And that's the hook the hypervisor needs to do the emulation. So, all right, maybe Intel should do a microcode update to say, well, don't cause traps to the hypervisor when you run SMX instructions. That'll guarantee they get run without being interfered with by the hypervisor. Well, that's not such a great idea either, right? Let's think about cloud-hosted infrastructure. Say I have an instance of EC2. If I run this user space instruction, get sec senter, do I really want it to kick the hypervisor out, put it in a trusted state, and put the real hardware in a trusted state and run the code I tell it? That would be a generic VM breakout technique, right? So that's like really bad. So instead of that, Intel decided that we ought to notify the hypervisor that someone's trying to run these instructions and let the hypervisor decide what to do. All right, so if I'm a cloud hypervisor, I can just respond with an error, say, yeah, that instruction's not supported. You can't do that in this virtualized environment. By the way, I think that was the right decision, right? So the hardware implemented it the right way, but it was a fundamental decision that had to be made. All right, so I want to shift gears a little bit and talk about AES and I. I'm looking at the same kind of setup with the hypervisor rootkit, saying how can we use that to intercept these AES and I instructions and undermine the integrity of the encryption. So quick background on AES and I. These are native instructions added to the CPU to speed up the process of encryption and decryption with AES. So it works well, gives orders of magnitude performance increase over a pure software implementation of AES. There's a set of instructions added to the hardware to do this, to do things like key gen assist, so for generating keys, for doing rounds of encryption and decryption. They actually have special opcodes for decrypt last round and encrypt last round. And it makes use of the XMM and the YMM registers, like the 128-bit and the 256-bit native registers that were already there in the CPU. Important thing to note is that your default crypto libraries, right, both in Windows and Linux, WinCrypt and libcrypt, things like that, nowadays all use AES and I as long as they're on hardware that supports it, which is pretty much anything modern, anything current. So what we want to do is find a way to cause traps or VM exits to our hypervisor rootkit anytime AES-NI instructions are executed. So we want to put the CPU in a state where that happens. We want to configure our hypervisor rootkit to catch those events. And then we can kind of play man in the middle, right? Allow the encryption or decryption to happen, but spy on the keys that are being used. Log or store off the unencrypted data. So right, either before encryption or right after decryption, get that plain text and capture that. So that's what we're going to do. And so the first question is, how are we going to get notified when these instructions are executed? How are we going to trigger those events? Unlike the get-sec-senter instruction that automatically traps to the hypervisor, the AES-NI instructions are user space instructions. In a sense, in terms of privilege standpoint within the CPU, they're not a whole lot different than add, subtract, multiply, divide. They're instructions that can be run from user space, and they don't need to notify the hypervisor. So we had to say, all right, how can we get creative to cause these traps? So start by looking at the pseudocode in the instruction set reference manual and say, well, what kind of events, what kind of exceptions can they generate? So all right, they can generate exceptions type 4. All right, let's flip a few pages in the instruction or the Intel manual and go and look, and we pull up this table on what exceptions type 4 means. And there's a bunch of rows here, a bunch of ways they can generate exceptions. Some of them have to do with the values that are in the registers at the time the instructions are executed. Okay, those aren't super relevant for us. Hypervisor doesn't control the operands that the software is using. But then there's a couple I circled in red that are dependent on the state of the CPU, specifically bits in the control registers. Well, that's cool. The hypervisor can manipulate the control registers and has free reign to do so. So that looks interesting. Let's try that, right? So digging down a little deeper, looked in control register 4 specifically, and the bits that we end up toggling are the ones that turn on or off the XMM and YMM registers. So for backwards compatibility, you can turn off those registers, right, so that older software runs like it normally did. When you want to enable access to them, you have to set these bits to turn on those features. It allows those opcodes to now exist, and the system is happy. So what we can do is turn those bits off, and that will cause any instruction using XMM or YMM registers to cause an undefined opcode exception. And then, cool, we can use the hypervisor to configure the system to route those exceptions to the hypervisor instead of to the kernel. Bam, now we get notified when these instructions are executed. Important to note, in this case, we get a bunch of other stuff too, right? A bunch of vector computations, anything using XMM or YMM registers. So we got to do a little bit of filtering based on the opcode when we're doing our logging. And so if we look here, an example for OpenSSL, put together a quick example of generating a key, encrypting text, and then decrypting it, right? So we're kind of running through that whole life cycle. And on the left-hand side, we see the serial port output from our hypervisor. And on the right-hand side, we see the output of the OpenSSL script that we wrote. And so the first thing we see from the hypervisor output is the AES key gen assist. And not sure how well you can read it in the back, but one of the operands to that, the value directly in one of the XMM registers, is the actual key, the AES key. So that's kind of cool. We don't have to go looking through memory to find this, right? It's just handed to us directly in a register, directly in the operand for that instruction. Okay, so we can make note of that. We let it go ahead and do its encryption, and then do its decryption. And then the next thing I'm pointing out here is AES decrypt last. So it does multiple rounds of decryption and can be configured. AES can do different block modes and things like that. Don't have time to get into all of those details here right now, but bottom line is when it gets to the last round of decryption, we can look at the result coming out of that computation. Again, that result is provided directly in a register, so we don't have to go around poking in memory trying to find it. It's right in a register, so we can make note of that result. And then a few instructions later, we see the XOR go on, and the XOR takes this initialization vector that OpenSSL used as one operand, the output of AES decrypt last, and the result is actually the bytes of our plain text secret message that we had provided. So this is pretty cool, right? We don't have to go searching around memory for keys. We can grab them during like key genesis. We can grab round keys directly out of the registers when it's doing rounds of encryption or decryption. We can even grab the plain text right out of the registers. So what's the catch, right? Like, sounds a little bit too good to be true. And the bottom line is it's performance, right? Because we couldn't route just the AES instructions, we end up with a bunch of other stuff. There's a performance impact on the system in this case. My proof of concept here was not optimized, right? Something I put together in about a week and a half. And the performance impact is noticeable. The system is noticeably slower to the user. Could it be optimized? For sure, right? Could spend a lot more time, try and minimize the performance impact, try and do more efficient filtering and things like that. But at the end of the day, you're still going to incur the penalty of these context switches to the hypervisor and back for more instructions than just what you're looking for. But it is possible to do. All right, so now let's talk a little bit about who's affected by these types of things, by undermining AES-NI and TXT. So there's a variety of systems that use AES-NI for sure, desktops, laptops, servers. But when you put these two sets of technologies together, cloud infrastructure is the one that kind of is impacted the most, right? So just as like a thought exercise here, what if somebody gets into the cloud infrastructure, either uses like a VM breakout technique, right, and gets execution in the hypervisor, or maybe a malicious insider that works there and kind of loads some code on, and bypasses the root of trust, makes some changes to that hypervisor to add some malicious bits in there, and then decides to start snarfing up all the AES keys from everything going on, right? That means everybody that's connecting in remotely, using VPN, using SSL, maybe using disk encryption to store their data securely in the cloud, they could be at risk. And I do want to note that the techniques that I'm talking about here are not operating system specific. So I talked about some Linux implementations, but what we're really doing is architectural. It's based on the way the architecture works. We also have it working and have demonstrations on Windows as well. Same code base, no changes, right? It's hypervisor rootkit. It's not dependent on the operating system. All right, so how will I know if I'm affected by this? Will I know? Well, it'll be hard, and probably not. When it comes to AES-NI, many sysadmins don't even know whether their software is using the native instructions or using a software implementation. And I'll conjecture that many developers also don't know. In pulling together my proof of concept here and doing this research, I was like, all right, well, let me find an interesting test case to start with, right? What's going to be the easiest thing that I know for sure is using AES-NI? It was really hard to do that, to find any documentation that said one way or the other. Because a lot of applications are just using a library, right? And you call a library function to do AES encryption. Do you know if that library function is using the native instructions or as a software implementation? Not really, right? So because of that, a lot of people aren't even sure if they're using it. Based on my experimentation here, and digging in a little deeper to those default libraries, I would say the answer is yes. It probably is being used because by default, the libraries will use it when the CPU supports it. When the CPU doesn't support it, they'll fall back to a software implementation, and the caller of those functions doesn't know the difference. There'll be a performance increase when the native instructions are there, but other than that, there's no indication one way or the other. And as far as TXT, right, if you're someone that uses that for a server platform, it's really complex. It's an impressive technology, but there's a lot of pieces to it. A lot of hardware changes, a bunch of specifications that go along with it, hardware from multiple manufacturers, multiple pieces of software that all have to come together perfectly to really put you in that secure state. So let's move on and talk about what we can do about it. What are some steps we can take to protect ourselves against these kind of attacks? So if you're really paranoid, right, and you want to encrypt data in the cloud, and you're like, well, I don't want to be subject to this kind of attack. I want some way around that. Your best option is to use a software implementation of AES. Don't use the native instructions. Because what that does is makes the job of a hypervisor rootkit a lot more difficult. So what do I mean by that? I think about it like, where's Waldo, right? So on the left-hand side, we can see everything in that graphic, right? Nothing is blacked out. Just like the hypervisor can see all of the bits and the bytes in the system that has the privilege to read anything in memory. But finding Waldo in that graphic takes time, and it's hard, and it's not easy. Compare that to the graphic on the right-hand side, where there's like a big circle and an arrow, right? And that's like when we get these VM exits, we can configure the CPU to notify us as a hypervisor rootkit and like point over here. It's like, well, that makes the job a lot easier. And yeah, in the circle, it's not just Waldo. There's like 2 or 3 other people in there. So we have to do a little bit of filtering, but still way easier to find what we're looking for on the right-hand side than the left-hand side. So one of the things you can do is hide in the noise. Using a software implementation, making it harder for the hypervisor to configure the system in a way that it can have the hardware do the filtering for it, and leverage this challenge, which is called the semantic gap, where the hypervisor has to try and make sense out of everything and find exactly what it's looking for. All right, so TXT and sealed storage. The reason this attack succeeds, the reason the hypervisor rootkit can undermine TXT is because sealed storage is not used. And my conjecture is that sealed storage should not be optional. It's kind of considered an optional part of the platform, but without it, you have no way to guarantee the system is in a trusted state. So if I'm going to use sealed storage, if I want to implement that, what are some of the challenges to doing it the right way? Well, first thing is you have to decide what secret you're going to seal in the TPM. Right? So the first pitfall that you can run into is picking a secret that the attacker can guess. Right? So although I can't undermine sealed storage as a hypervisor rootkit, I can emulate the TPM unseal operation. It's just that the real hardware, the real TPM, is not in a state where it will release its secrets to me. I'm letting software talk to a virtualized TPM. So if I don't know what's locked in the vault inside that TPM, then I can return some data to you when you say TPM unseal, but I'm not going to have any way of knowing what that data should be, unless you chose poorly and I can guess what that value is. If I can guess that value, I can return it and you won't know whether it came from me as the hypervisor rootkit or from the real TPM. So you want to pick something that, that can't be guessed. Okay, so that's number one. Number two, you want to make sure that the value that you're storing there isn't kept like around at runtime. Because if I compromise your system at runtime, and I can find that secret in RAM, in memory somewhere, and I save it off, then I can also report that back to you on the next boot, and again undermine the root of trust. So you want it to be something that doesn't hang around very long, something that you use just to prove you're in a trusted state at boot time, and then you don't leave it hanging around. The next thing you need to do is make sure you extend the PCRs after you unseal your secrets. So again, if you think about it as like the combination lock on the safe, right? If you open the safe, take out your secrets, and you leave it open, I can walk in behind you and I can just do TPM unseal myself, and I can read the secrets right out of the TPM. And this is a common pitfall I've seen as well, where do everything else right, and you pick a value that they're not going to guess, and you don't store it in memory, but you didn't do an extra extend on the PCRs after you extracted the value. So the attacker can just go right back to the TPM and read it out. So make sure after you read the value out, you do another extend on one of those PCRs, which is like spinning the dial on the lock of your combination lock. Yeah, and again, so the bottom line is be careful about what you're sealing in there and how you use those values. A lot of people want to use this for disk encryption and say, all right, well, I can make sure the system won't boot, and load my home directory if all my data, is on the drive is encrypted and the key is stored in the TPM. Just have to be careful if that's the key that you keep around at runtime so you can continue to access the disk. The attacker can find that and fake that, using that both to protect your data and to ensure you're in a trusted state. You're putting a lot on one value and perhaps opening yourself up to compromise. So what's my recommendation? There probably are several ways you can do this safely. But what I recommend is using a value that's displayed to the user at boot time only, to authenticate that trusted boot actually worked. So you're going to take, it could be a picture, it could be a string. Think like when you log into your bank, right? A lot of them, but you'll enter your username before you type in the password, like they'll show you a picture or some text that you typed. You want that kind of thing in the pre-boot environment here. Show the user something that they created that's unique to them to prove the system is in a trusted state. Have them hit enter to continue. Right? When they hit enter, wipe that secret out of memory, do another extend out of to the PCR so that that's not accessible at runtime after that, and then allow the system to boot the rest of the way. And you can combine that with full disk encryption and things like that. But this is the way that you can really attest to that user that the system's in a secure state. And you can do the same kind of thing with remote attestation. And instead of displaying it locally to a user, at that point in time you can attest to your remote server that you've configured properly. All right, so that concludes my talk. Want to thank everybody for coming, and at this time open it up for any questions.
Hi. So out of 100 sysadmins or 100, how many people will know this? I mean,
will know about the technology?
Well, I mean, to implement the kind of things you talked about here. So it makes sense having heard this brief. But I'm just wondering if you were running along fat, dumb, and happy saying I got a really good set of security people, would most of them intuitively know this, or would this be something you need to hold special training classes on, or what?
Yeah, so this is not something most sysadmins will know. They might know the name TXT and tboot. Things like ESXi can use tboot by default. Sysadmin might check a box to say they want to use that technology. They probably don't understand the inner workings very well at all.
Right.
So yeah, it would be something to go to training on, to learn about, and so I've been talking with Intel, and the hope is to get an instantiation that uses sealed storage that's out there, open source, that can be kind of turnkey, so that we can point sysadmins to that to be able to use it.
And the hypervisor you talked about, a hypervisor root is something routinely available that most attackers would know about.
So it's a type of rootkit. It's been around for a while. Blue Pill was kind of the first one that we heard about. So it's a technique known to attackers. How widely known is it? It's certainly not the most common type of attack, but it is kind of known in community. Yeah.
Thank you.
Yep.
Yeah. I just recently attended the iOS security kernel that they had, which really looked like a reference monitor, and so that really brings the question just at a high level. I mean, it just seems to me that TXT is just not that useful, given that in the end there's so much in the trusted path that has to be trusted, so to speak, and it's just not there. I mean, you got the hardware, but then everything else is still dependent on the software, the operating system, the hypervisor.
Yeah, so
I mean, we're looking at it in a data center context, trying to secure our VMs and in an open stack environment, and it's a really tough problem.
So it is a really hard problem, and I should say I'm actually a big fan of the technology. It's really difficult to use. It's really complex.
Right.
But the problem that Intel is tackling here is much larger than like the problem Apple is tackling on their devices, because they want to be able to do this when they don't control all the hardware. There's a bunch of third-party hardware in there. So they're tackling a huge problem here. And I think what we have are some good tools for the job, but there's still some work to bring it up to a level that makes it easier and safer for people to configure and use. And I think large data centers is really where this makes the most sense, because there's enough value there to spend the time to get it right. As compared to just my laptop, it's probably not something most users are going to play around with for a single laptop, but for some critical cloud infrastructure and things like that, it's worth the time to get an implementation that works and that's right. And even though it's complex, there's a lot of moving parts, there can be a huge benefit when you do it the right way.
Yeah, I mean, I can see that there's some benefit here. It just seems like it's not enough, really. I mean, you need a secure processor. You need some way of reaching back into the I/O and controlling the I/O of the the hypervisor and I guess the interrupts and all that stuff. I mean, I think there has to be a little bit more. Well, I mean, iOS I think went a long way with their work. I was really impressed. So this seems like just too small a piece. So, but I understand what you're saying. Yeah, it's better than nothing. So.
All right. Yeah. Thanks.
I had a question about the AES-NI hijacking.
Sure.
So you're manipulating the bits in the control register, if I understand correctly, to turn off the XMM and YMM. Is there a way that the higher level OS that's being hijacked can check those control registers, or can the hypervisor just lie about those values?
Yeah, so the hypervisor can lie about those values. It's actually kind of inherent and an easy thing to do in order to support multiple VMs with different settings. Like hypervisor inherently has the ability to have one set of values in the hardware and a different set in what's called a read shadow. So when the guest operating system reads the register, they can see one value, but it's different than what's really in the hardware. So that's how we implement it. So when the CPU checks for support, it thinks that it's there and it's turned on, but it's actually not.
Okay, thanks.
All right, and I think with that, I'm out of time. I'll be around. I'll be out in the hallway. If anybody has other questions, happy to talk to you then. Thanks again for attending.